Hello, welcome to another episode of Funding Philosophies, a series where I talk about various philosophical and scientific subjects from my own perspective. So today I'm talking about physics. So I'm going to try and make this quite as informative as I can do, given that I'm not a physicist per se, but I do have a rather deep developed interest in it, as it were. I've never studied physics formally. I've always maintained an interest in it throughout the years, from being a kid. So when I was younger, I used to be very interested in the stars. It all kind of roots back to that, really. The wandering, pondering of the stars above, and looking at space and pondering where I come from as well. All those big questions have always driven me on some level. But this is not about me per se, so I want to try and go into physics in a nutshell is essentially the study of reality in the universe and describing nature through the mathematics, which is a language we've developed as human beings to understand the world. So everything from, like in terms of mathematics, we drew out algebra, calculus, as ways to understand what this world around us is, beyond just the man-made stuff like this room I'm in, the computer, everything else. That which emerges from nature, this almost chaos. Because I think a real key idea in physics, I don't know how much this often explains, is that really physics is about determining the order of nature. Because nature, when you think about it in the abstract, seems chaotic. It seems like there's no patterns, there's no underlying order. And what physics is about is unveiling that order beneath the presumed chaos, which is why for me it is the most beautiful and enduringly interesting science for me personally, is because it's about revealing a kind of almost divine order, but without that kind of idea of the creator, I suppose. Though if he is there, then we find him, then that's an interesting question. That's one that's many physicists have, spent half their lives or all their lives kind of wrestling with. Even to Einstein himself, he was his idea of the divine was generally kind of what is commonly known as a pantheistic one. That being, he saw nature as a kind of a god, as a nature essentially. Because Newton as well himself had a very complex relationship. I'm just mentioning these names without really explaining them, so I don't know who's watching this. So obviously a lot of modern physics roots back to Newton. Newton, who discovered how gravity works in terms of Newtonian physics, and how even celestial bodies orbit around the sun. There's Galileo, of course, in terms of cosmology, who determined that or observed that we were revolving around the sun and not the Earth. The sun revolving around the Earth, which was the traditional view up until the point of Galileo. Galileo suffered quite severely, as I'm sure many of you will be aware. Rooted back further, and my knowledge on this is a bit lacking, but there's Hypatia. I'm trying to make this balanced at least. Hypatia, who was involved in the Library of Alexandria, so one of the most famous early world kind of physicists. Who was also a woman. So she is involved in a lot of cosmological observations, and I'm kind of going off track of it now. I know that's not that, probably will be a bit tokenistic, but I'm trying to be inclusive here. Okay, yeah. So where are we? Galileo determined that. Newton, there's a famous apple on the head, very interesting figure in science, very eccentric in a lot of ways, never had sex apparently. Shit, man. That's a sucker. But that's funny, you get a lot of figures like that in science. Well, not a lot actually, that's a massive overstatement. You get a few these kind of very exceptional eccentrics in science who seem to have very closed off lives, but anyway, that's a tangent. I'm not going to bother going down because it's pointless. So yeah, and so you had Newton and Newton's kind of model of the world reigned for a long time until Einstein came along and kind of broke it all. So Einstein, with his theory of general and special relativity, so general relativity deals with how large bodies, how gravity and space and time correlate with each other, and a lot of it has to do with light as well. How so Einstein determined that there's a universal constant, which is light. So that's the speed limit of the universe, and how space is basically told how to be shaped by gravity. Mass warps space, which then, in terms of like the orbits, galaxies. In this example, the sun has such a mass that it warps the space around it into a shape, and then the planets orbit around that base due to the warping of time and space. I might have butchered that a bit, but that's my general understanding of how general relativity functions. Special relativity, I can't remember exactly the specifics of that. I'll try and look it up now actually, it is a massive cheaty way to do it. Like I said, I'm not that's a relationship between space and time, yeah. So how space, there's a thing you'll hear about a lot, which is the space-time continuum, which is the Einstein's idea about how space and time are intimately linked. But again, I'm not an expert on this. I'm just going to try and mention a few things and go off on a few different tangents. So Heisenberg, as in certainty principle, that deals with quantum mechanics, which I don't think I've mentioned yet. So quantum mechanics is the world of the small, in terms of atoms, particles, quarks, etc., etc. Obviously we have matter, which is all around us. We are composed of it. Everything around us is composed of matter, chemical mixture of chemicals, molecular structures, etc., etc. Matter is just the stuff of the universe, essentially. There's also interesting stuff called dark matter, which might be out there, which accounts for like a lot of what the universe is, but science still doesn't really know what that is, but that's going to help myself with it. So matter is just the stuff of the universe, it's the substance, it's the matter. It's kind of, I think it must be a Greek rooted word, I think. Not 100% sure, but I'm pretty sure it is. But yeah, so matter is the stuff of the universe. It emerged, as far as we can tell, the universe and all matter and all energy and all the rest of it emerged from an event called the Big Bang, based on observations and the data that we have from our various tools of observation. The universe is expanding. All the data that we have been able to, science has been able to process, has shown this again and again. This is due to a phenomenon known as redshifting, which is a phenomenon of light observed from distant stars. So this proves scientifically that we're expanding into something. We don't know what that something is. That's what has happened. So yeah, I was going to talk about the Big Bang, wasn't I? Sorry. The Big Bang is the theory for how the universe came about. So it's a singularity in space-time, which is singularities. Well, I don't know if singularity is the right term. It's a it is. It's an infinitely dense point in time before time and space, which time and space emerged from. So I remember reading that it was basically like something like 0.1 millimeter of space, they think, and then just time and space emerged out of it. There was this Big Bang state. It was a kind of hyper complex state prior to time and space as we experience it now, which is unfolding in a linear manner. So time is obviously, from the perspective of us and our minds and our consciousness, unfolding forwards, going forwards. It's not going backwards. It's progressing along quite a linear route. So this is A, on the left, this is big on the right, it progresses this way. Now there could be universes, parallel universes, where it goes the other way, B to A, or vice versa. Dimensions. So there's, you have a two-dimensional. Let's talk about. So two dimensions are a product of. I guess so three-dimensional shapes. Well, okay, so start this one generically. Two-dimensional shapes are obviously representations of 2D. I don't really need to explain what 2D is. I think really it's just like a shape or a form with a certain amount of sides. So in Pythagoras would be how to calculate three sides of a triangle. Pythagoras' theorem, which is an equation which shows how to calculate the right angle sides of a triangle, essentially. And then 3 dimensions is solid three-dimensional objects. So like you know what a 3D object is. 4D is, I think it's the dimension of time and space and how all that relates to the three-dimensional world as well. 5-dimensional, I think, is an object which can curve into itself. I'm probably butchering some of these descriptions, it's quite late, I apologise. But so I think a tesseract is an example of a 5-dimensional object. So I'll put a video up actually of a tesseract on this video. So it is like a cube. So this is a good example actually. If you've got a 2D square, and then you've got a cube which is 3-dimensional, and then a tesseract would be a cube, and I can't obviously describe it with my hands because it's impossible, but it's a cube that kind of folds into itself and then it makes itself out of itself essentially. So yeah, that's that. And this is a real area that I need to expand my knowledge on, so I probably did butcher a lot of those descriptions. There you go. What else? So there's some interesting cosmological theories about different ways that the universe is going to end up, or it's going to, where it's eventually going to go. In physics, you have a concept called entropy, which is to do with the amount of disorder in closed systems, and also energy, and second law of thermodynamics, which is how much order a little second law of thermodynamics is how predictable it is for how the amount of time. I'm butchering this completely. I apologise. Entropy in general is the amount how energy winds down in a closed system, basically. So let me just explain it another way. Sorry, I am jumping around quite a lot. So for example, a really easy example is we've got a cup of coffee. So say this is full of hot coffee. The energy state of that coffee is rather predictable, given a certain amount of time. So there's coffee in there, just imagine it because it's not there. But there's coffee in there, just imagine that. I put it down, I leave it, forget about it for 2 hours. When I come back to it, obviously the heat energy has wound down, so it's become cold. Over a given amount of time, that will decay into, as in like you get mold in the cup from the milk. So yeah, that's it. Entropy basically is everything in the universe tends to disorder in terms of kind of breaking down over time. So one recent thing I've been reading about a bit, not a great deal, but a bit, is chaos. And chaos theory and chaos math, and this is a new area for me. I know nothing about it really apart from very basic fundamentals of butterfly effect, whichever refers to. There's also in chaos theory, so I've started reading this book, which is actually here. James Gleick, so I put it on the borrow from someone I know who's a physicist. Unless he, where I'm up to, the Lorentzian, yeah. So this is quite interesting. It's kind of roughly related. I know I've kind of jumped around a lot here, but it's kind of, would expect this is physics. So we've got Lorentz, who, again, this relates a lot to entropy, kind of about the idea of a certain kind of disorder and how, but in his, what I remember from reading this is about how to predict, kind of like using computers, the underlying order within supposed chaotic systems. For example, so you've got the Lorentz attractor there, which I just love it as an image. So Lorentz attractor, so yeah, revealing structures hidden within a disorderly stream of data. I can't really, we've got 5 minutes, I don't want to go too deep into it, and I don't have the required deep knowledge of it. Another book I read a while ago was Roger Penrose, who was talking more about possible models for the universe's end and beginning. I didn't read all of it though, I haven't finished that book. But that's quite interesting. He's a contemporary physicist, I think, at Cambridge. So I've covered quite a lot there, but I need to carry on. I need to do a bit more. Big questions in physics at the minute. Obviously you've got the God particle CERN particle accelerator, which is basically looking for, well, they've got it, they found it ages ago actually, which is the Higgs boson, which was a so-called God particle in the standard model of physics. I should have explained this ages ago. The standard model of physics is just a way of describing all the atoms, quarks, all the other names for different particles and atomic structures which occur in physics, in the standard model of physics. I'm not an expert on it though, so I can only really describe basically what it is. I don't know the actual, all my neutrinos, my quarks, quarkons and all the rest of it yet. It's something I really want to probably expand on a bit more. I do have a natural interest in it, and I kind of have a half decent way of learning the rest of it. Some science books I would recommend. There's a really interesting, so I've just been reading more popular science by it really. 17 Equations You Must Know, which is a mixture of mathematical but also physics-based equations. Michio Kaku Hyperspace is a really interesting book to read. Obviously, Stephen Hawking's History of Time, though I've not read it myself, but obviously it's a classic in many respects. And what else? Michio Kaku is a really good place to start. What else? James Link, Roger Penrose. I have a Kurt Gödel book here, but it's mostly incomprehensible to me. This is more to do with, this is mathematics. It's about an arithmetic system. This is still mostly incomprehensible to me, to be honest. It's very interesting, but I can't get my head around it yet. So this is the book I've been lent. Yeah, but anyway, I've gone off topic a bit now, so I'm going to end it here because we've wasted 20 minutes. That was a run through physics, how I see physics, a kind of big kind of overview of a lot of it. I've probably got things wrong because it's late, and like I said, there are gaps in my knowledge in terms of physics, so I apologise to any of the physics nerds watching this, and I will work on ways of expanding my knowledge, I guess. That is what I hope to do, hopefully in some small way in the future anyway. I'm kind of more like a hobbyist physicist, I suppose. I watch a lot of YouTube videos on physics when I'm bored and absorb as much as I can, but so in my small way I'm trying to give back something, even though it's just a kind of very rambling version. So thank you for watching if you've got this far, and yeah, see you in another funny philosophies video. Au revoir.